So, good afternoon, everyone. Good afternoon from Hellenic Mediterranean University in Crete, and on behalf of the Athena talks that they are organized through the European University Athena, we are very glad to have with us Nick Petropakis. Professor Nick Petropakis, I will provide a few information about the short bio of our today's speaker. Nick Petropakis has completed all his undergraduate and postgraduate studies in Greece. He was undergraduate studies in the University of Athens. Then he moved to Economic University, and then he implemented his postgraduate studies, in Greece, in the University of Piraeus and the Economic University of Athens. Then he moved for his postdoc to Georgia Tech in the US. And now we can find him as an associate professor in Edinburgh, Napier University in Scotland. I have to say that, I'm also very happy that we have a speaker from Scotland, since I have done my PhD as well in Scotland. And this one is my favorite small country, Scotland. So Nick Petropakis is an associate professor of cybersecurity at the School of Computing of Edinburgh, Napier University, and a fellow of the HEA. It's an acronym that I will let Nick later on to present to us. He's also a core member of the Block Pass Identity Laboratory. Dr. Petropakis has a strong research background in attacks against machine learning. His current research interests include adversarial machine learning, trust and privacy using distributed ledgers, a technology, advanced cyber attack attribution, and data science applied to cybersecurity and IoT device security. Dr. Petropakis is leading the integrated apprenticeship scheme Bachelor in Cybersecurity, which is the first in the UK to receive full accreditation. He's teaching cyber-related graduate apprenticeships degree, both running in Scotland and in England. He's also the external examiner of the American College in Greece, covering the Bachelor in Information Technology and Bachelor in Cybersecurity and Networking programs provided by the Open University, and the lead external examiner for the Master Cybersecurity in Newcastle and London campuses of Northumbria University. So we are very happy to have as I said, to have with us Nick Petropakis, and today's lecture within the framework of the Athena talks is Truth or Dare, Attacking the Artificial Intelligence. So Nikos, and I would like also to thank Evangelos Markakis for the introduction. The floor is yours, and we are very happy, and we are looking forward to attending your lecture. Thank you.
Thank you for the invitation. I think my screen should be visible now. As Costa said, my name is Nikolaos, Nick for short, Petropakis. Since I went to Georgia Tech for my postdoc, I had to chop my name in order to make it easy to be pronounced after a lot of failures in the presentations that I gave as PhD student. For the past 5.5 years, I've been working for Edinburgh Napier University. We are one of the modern universities and the #1 modern university in Scotland. You will find us in Edinburgh, where we have 3 campuses. Currently, I have the position of I am an associate professor of cybersecurity, and I'm also leading the teaching and learning of the cybersecurity and systems engineering group within the School of Computing Engineering and the Built Environment. Since last year, we merged the computing and the engineering together. That's why we have such a long name. Today, I'm going to talk to you about one of my major interests, research interests, and one of the domains that I've been working on with quite a lot of my students for the past 4 years approximately, since 2019, and I will get to that, how the journey started. The contents of what we are going to talk about, just to briefly summarize them. First of all, we are going to talk about machine learning in general, then the threat landscape, taxonomy of attacks, a proposed taxonomy of attacks against machine learning, a use case about the Internet of Things intrusion detection systems, a use case about malicious URL detection, and another use case about financial series models. At the end, we will draw some conclusions with regards to what has been presented until that time. So, first of all, what is machine learning? Okay, we live in an era where artificial intelligence, machine learning, a lot of we have a wide spread of different IoT devices that we are using daily. Our phones have become way more intelligent. Even the devices that we have at our home, we are talking about smarter fridges, smart ovens, everything is getting smarter nowadays. So machine learning is there, a lot of models are being implemented. However, we all have a different perception for machine learning depending on our background, depending on when we grew up. As a child of the 90s, influenced by the Matrix movies, I wouldn't encourage you to watch the last one, it was terrible. Stay with the original trilogy. This is what it crosses my mind when I hear the wording machine learning, and this is what I had in my mind until I had the chance to attend one of the machine learning classes in my undergrad, postgrad, and later on apply it. For the earlier generations, being influenced by the Terminator movies, this is what machine learning is for them. And I'm talking about the 80s, the 70s. But if we go a little bit back, and if we ask, for example, my mother, who's a Greek language teacher, and we talk to her about machine learning, this is what is crossing her mind most probably. A machine that it's literally studying something. However, when it comes to the real definition of machine learning, and you see that Wikipedia, IBM, Stanford, even the Cambridge, the dictionary, they all collide with each other. We are talking about a science that brings automation and includes data and algorithms which perform actions on top of those data and present to us some outputs that are automated, and in most of the cases, because in some cases we also have the human involvement, in most of the cases we don't have to supervise them in order to get an output. Machine learning is a branch of artificial intelligence. So we have reached an era that, although they differ, the way we use it in our everyday life is equal. So we say AI and we mean ML and vice versa. It's not that accurate, but it's not that distant as well, as you can understand. And of course, it has a lot of applications. Applications that we use in our everyday life and in the scope of cybersecurity is intrusion detection, first of all. We want to keep ourselves safe from malicious software or from malware. We want to keep ourselves safe from cyber attacks, and that's why we use intrusion detection tools. Then we have the spam filtering, and this is usually applied in our emails. We want to get the emails that are normal, benign, from the people that we want to talk to, and we don't want to get some advertisement. We don't want to get emails that are out of scope and so on. Visual recognition and biometric authentication, this is applied in our life through our phones recently, and of course maybe through the place that we work. We can be authenticated even in Windows via our facial characteristics. We can use iris recognition if we are talking about high security premises and so on. The problem comes from the fact that we do an assumption when we use ML systems. And that assumption is that the data sets that we are using are representative and they are also trustworthy, which means that the end result, the output we get from the machine, it's representative of the real world. It's absolutely connected to the real world, so it has a real perception of what is happening out there. However, and this is where the problem starts, because of that popularity that the ML systems have received during the past decade, they became also very attractive to malicious actors. So from their perspective, they want to influence the decision-making algorithm that we are using in machine learning, and they can do it in two ways. They can either target the data that we use to train the algorithms. So in that case, if we use really bad data, we create a wrong perception about the world to the machine, and this is what we like to call poisoning attack. Or they want to force the model to misbehave, to redivert to another desired output. This happens through the testing phase, and this attack we like to call it evasion. The end goal of the adversaries is to decrease the overall performance. They want to cause targeted misclassification, or in general, bad behavior. And now coming to the adversarial machine learning. When it comes to adversarial machine learning, most of the time what is crossing our mind is the attacks against machine learning, which is not true, because essentially it's the study of effective machine learning techniques against an adversarial opponent. So it's more to the defensive point of view rather than to the attacker's point of view. Saying a few more words about the attacks that we already analyzed. When it comes to the evasion attacks, there the adversaries want to influence classification during the testing phase. So after we have trained the machine, and in order to produce the wrong system perception. So they need another output rather than the output that we would receive anyway. And they want to achieve misclassification in that case. Well, in the poisoning attacks, the difference is that they influence the input data, and this is how they are creating a problem to the classification, because they are feeding the model with a flawed training data set. In this case, they can completely distort the classification function during its training, and that they can divert the output of the system in any way they wish. And here you can see an example with a car that is self-driven, okay? One of the functions that we want the self-driven car to achieve is the speed limits. They need to be able to recognize the speed limits and perform and reduce the speed or accelerate according to the limits. Because in any other case, it's not only that they will malfunction, but we will have accidents, and that accidents can impact the greatest asset of all, which is the human life. So just to understand the difference between the poisoning and the evasion attack, in the case of the poisoning attack, we feed the model the information that when you see 70 is not actually 70, for you, the translation is 90. We can do it. It's perfect. We, of course, need to have access to those data, the training data, but we can do it. This is how we create the wrong perception, that 70 is not 70, is 90 or another speed limit. So the car will accelerate, an accident will happen. Now, there is another approach. We can distort the actual tag. So my colleagues in Crete know that some people like to use the speed limiters for targeting practice. So if we fill the tag with a lot of bullets, in that case, it means that it stops being recognizable in 70 and it's recognizable like something else, which might be 90 in this case. And that's the evasion attack, because we don't care about the training data. We care only about the output. And by altering the quality of the tag, of the speed limit tag, then we can influence the decision-making of the car. This is a taxonomy of attacks, and I will get to how we came to propose that taxonomy. It was back in 2017, a couple of years before we released the paper of the taxonomy. I was discussing with some colleagues. None of us were machine learning experts. We were using machine learning in our experimentations, but applied. So we had nothing to do with algorithms or whatsoever. And one of them came with a brilliant idea, and he said, you know what, I have an amazing idea. We will try to investigate the area under the scope, under the lens on someone who is not relevant, and convey that information to the rest of the community. And my initial idea was like, that might be wrong, that might be flawed. And he said, no, this is the proper way for someone who wants to engage in the area, because it's becoming more and more popular. And because we are not experts, it's going to be more comprehensive than someone who takes things for granted. So we did try it. I led that effort, and we came up with a taxonomy, which is not completely new as a structure. It relies on the literature, but we enhanced it in some elements that I'm going to talk about. In a modern taxonomy of attacks against machine learning, we recognize two stages, the preparation stage and the manifestation. In the preparation stage, where we try to prepare the attack to be effective, we see that we have the attacker knowledge. So the attacker can either have full knowledge of the algorithm, partial knowledge, or no knowledge. White box attack is the full knowledge, gray box is in the middle, the partial knowledge, black box is no knowledge at all. They want to influence an algorithm. The algorithm can be a classification algorithm, a clustering algorithm, or something in between, which is using both of them. So it's best of both worlds, which would like to call hybrid. On top of that, we found out that game theoretical approaches are very popular in attacks against machine learning, and there's a reason behind that we are also going to talk about it later. The attackers want to be effective without wasting a lot of resources. So in order to minimize their effort and maximize their profitability, or the effectiveness in our case of the attacks, they have to use game theoretical approaches. And that's why you see it there. Then the manifestation stage, when the attack is actually taking place, we want to know about the attack specificity. So the attack might be targeted at a specific model or a specific part of the model, or it can be indiscriminate. The attack might just want to change the output without caring what is the model or any other detail. Then the attack type can be either poisoning or evasion, depending on if we are targeting the training data or the testing data. And what we also added compared to previous taxonomies is the attack mode. In our days, nobody works on their own, okay? And even the attackers, they have a really good support system behind them. Believe it or not, they are using corporate mechanics. They have line managers, they have goals that they discuss with their line managers on a weekly and monthly basis, okay? So nobody's working alone. And we have either colluding adversaries or non-colluding, with most of them being colluding, okay? We used to have denial of service attack, now we have distributed denial of service attack. So it's not anymore one man's game. And in this arms race between the attackers and the defenders, the more the merrier. Now, hopping to the performance impact of the attacks, we have false positives, okay? And when we talk about spam detection, we have spam mail and we have normal mail. If the attacker wants to increase the false positives, it means that they want to falsely label many normal emails, benign emails, as spam emails. Okay, so essentially things that we should read, we end up not reading them because they come to our folder as spam. And this can happen, the systems are not accurate. The other day, I sent an email to my class through our Moodle platform, and it ended up in my spam folder. If it did happen with my students, it means that most of them, and I'm talking about 90% of them, never got the email. So I was also forced to make another announcement through Teams there, just to keep their attention active, because I knew that something might go wrong. False negatives. In that case, the spam emails will be tagged as benign, as normal, and we will end up reading them and waste our time eventually. Both false positives and false negatives. So in that case, the attacker is willing to reduce the overall confidence of the system, of the spam filtering system, and make it useless. When we talk about the clustering accuracy reduction, which is something different compared to classification, in the clustering, because we want to put the data in our data points into groups, it's a little bit less straightforward, because the aim of the attacker there is to reduce the overall accuracy of the clustering algorithm. So it means that most probably we will end up, for machine learning experts, with a huge Death Star, where we don't know where the data are grouped together, and we don't really know which fits what, and the groups are not easy to distinguish from each other. And I will go to the first use case, the intrusion detection systems in IoT devices. The reason we were challenged and we were influenced to go down that path and perform some experimentations on this specific field was the spread of the IoT devices. So Gartner predicted that by the end of this year, by the end of 2023, we will have 48.6 billion IoT devices connected using 5G. Okay, the problem with those devices is that usually they have minimal computational capabilities compared to our workstations. Okay, and because of that, they are more energy efficient. They don't waste a lot of energy resources. But those limitations force us to have centralized infrastructures when it comes to intrusion detection systems that usually detect or adversarial activity through the network traces. And the reason is because we cannot do it individually with every one of those machines, although this tends to change. So we are trying to make more computations at the edge, but is not standardized yet. We are still using those approaches, and I don't think even if we go for edge computations, we will abandon these approaches, because they are more centralized and they give us a holistic overview of what is happening within our network perimeter. And because we are collecting massive amounts of data from that number of devices, it means that we cannot eyeball them, and we need to automate it, and that's where machine learning comes into the picture. We need to find solutions that are able to detect what is abnormal and what is normal within the network traces. And in that case, we are coming up with, we selected a data set that has become quite popular in the past few years. Back then it was in its first steps. BOT IoT dataset, which was created in a simulated environment from a victim and attacking machines. It has different attacks that are categorized into 5 classes: normal, reconnaissance, distributed denial of service, and information theft. You can see the numbers, the full amount. I'm also citing where we got it from in case you want to use it as well. And the 5% amount that we worked with eventually, because in order to process the whole data set, we needed an infrastructure that we didn't have back then, and we worked locally. And we believe that it was kind of representative, the 5% that we used, that we split in training and testing, and I will get to that as well. So we got 5% of the initial data set, which was massive, and we split that 5% into 2 chunks. 80% that was used for training and 20% that was used for testing. The approaches that we used was support vector machine, SVM, that is using a support vector classifier using a linear kernel, a trained artificial neural network, ANN, that had 1 input layer, 3 intermediate layers, and 1 output layer. And we used 2 attacks. The first one I'm going to explain because you will see that it's common throughout all the application domains that I'm going to talk about. And to be honest, it's the easiest attack that we can find in the wild. And this is what I'm encouraging my students to do as first step. So when we train a model, we provide labels. We want, in the scope of cybersecurity, we want the model to understand, the machine learning to understand algorithm, what is good and what is bad. And at the end of the day, to be able to differentiate them from each other. That's the perception we give about reality. So we provide labels. We say that this network trace is considered good, and this network trace is considered bad. If we flip that, and that's where label flipping comes into the picture, it means that essentially we create a wrong perception of the machine about reality. And that's how we enforce a poisoning attack. And this is the easiest we can do in terms of attacking a machine learning model, and especially when we have full access to the model. When it comes to the neural network, things can become a little bit more complicated, and you see that there are different steps that we can take with the fast gradient sign method attack, FGSM, and they are cited here. Here we have two algorithms because when it comes to the label flipping, we used two approaches. The first approach said that we randomly selected labels to flip, which is the easiest we can do from an attacker's perspective, res resources committed. But the second one, here the attacker is trying to become more effective, and we selected carefully the resources that we used, the labels that we used to flip, because it means that we had a better result. And this is something that is going to be reflected from the plots that we are going to check. And here are the plots. Okay, in the left side, you see the targeted support vector machines, flip metrics, and then the non-targeted. Okay, in the targeted, you see that especially the accuracy drops suddenly and compared to the non-targeted. But the non-targeted, it follows a standard pathway, dropping all the time, where in the targeted, this is starting to change. Honestly, in either case, don't expect the attackers to use a lot of resources. You see the flipping percentage, it's up to 50%. I can guarantee you that if someone has access, they will never reach that percentage. Usually, the magic happens between 0 and 10%. Okay, and if you think about it, it's around 5 to 7% in both cases, where you see the minimal resources invested by the attacker and the maximum output happening. Because from the 99% point something accuracy dropping suddenly to 75%, okay, this is a huge loss. It means that a lot of things are going through our filter, things that we didn't anticipate, which in reality are successful attacks. Of course, you can also see how that is being reflected with the recall score, precision score, and F1 score. In this case, you see what happened with the first gradient sign method. And again, we have the results on the left, the classification results with the non-targeted, and on the right with the targeted. And here in the first gradient sign method, you see that again there is no real reason to go targeted, because we achieve a good result, but not as that good of a result compared to the non-targeted, where we are not committing more resources to influence the model. Okay, because the drop is standardized when it comes to the accuracy, and again you see how much easier it is to use less resources and achieve the maximum outcome. And this is where the adversaries want to throw their attention on. And here we see multi-classification metrics. So initially we had a binary classification. Here we have a multi-classification, a multi-class. Again, with the influence of the fast gradient sign method, targeted and non-targeted. In this case, the results are pretty similar. Okay. I will hop to another case, malicious URL detection. In general, the World Wide Web, the internet, whatever you want to call it, has become an integral part of our everyday life. On daily basis, we visit a lot of websites, and some of those times we visit the wrong websites. This is something the adversaries take advantage from. So you see how a URL is being constructed. You see the protocol, the subdomain, the root domain, and the top level domain, and of course then the subdirectories and the file name. But the thing is, when I'm talking about mistakes, there are mistakes that they enforce on us and the mistakes that we do them accidentally. I will take the accidental part first to explain, and I will say a couple of things about that. So when we change the original domain name to something slightly different in order to serve a malicious cause, it's called domain squatting. There are many types of domain squatting, and the first type of domain squatting that was recorded was the typo squatting. When we talk about typo squatting, we mean about a domain name that has one letter difference compared to the legitimate domain name. A perfect example is, we all know trends like Nike or Coca-Cola and their main domain in the States, which is the .com. Okay, their international domain. It's easy for us when we type, and especially when we used to have the membrane keyboards, instead of COM to type CM. But that means that from the COM the top level domain, we are being redirected to the Cameroon top level domain. What happened in the past, some gentleman was very intelligent and he bought all of the popular domain names in Cameroon. And when the legitimate holders understood that this is happening frequently, they were forced to buy their intellectual property, basically, for lots of money. However, that did not include an attack. The problem is, after that happened, the attackers started creating those domain names on purpose to attract users, to accidentally fall on them, and then either fish them or acquire money from them, and so on. This attack became even more efficient and complicated. So from the typos, we went to the homophones. Whether the weather is good today, whether I'm going or not, it's going to be the same. They sound the same, but they are spelled completely differently. So the attackers use the homophones for domain squatting. And then the latest phenomenon that I had the chance to study at Georgia Tech was the combo squatting. Taking the original domain name and combining it with words, phrases, symbols, whatever you can think of to create something else. For example, let's take HSBC. It's an international bank. Many of us have an account to HSBC, okay, regardless of the country. If we get an email saying that you have to verify your login details and the domain name is hsbc-secure, and then whatever the top level domain name, depending on our country, because it's accompanied by the word secure, we are like, okay, it must be secure. It's HSBC anyway, and we have to do it. It doesn't easily cross our mind that this is an attack. And this is what the attackers take into consideration and they take advantage of. And that's how they attract sensitive information. So we have a lot of malicious URLs being there on the wild. They are usually short-lived, but there are others that stay for long. And we tend to visit them either accidentally, either because we are getting fished, or because of other factors. The truth is, we want to detect those URLs. And one way to do that is eyeballing. Then that's why we have a lot of public blacklists where people did visit those URLs. They saw that it's not okay and they reported it, but that takes time. So we rely again on machine learning models in order to classify the URLs, okay, and find what is benign and what is malicious. But the problem is that their performance is likely to be severely degraded with mild perturbations. So to have effective ML systems, it means that we need to maintain high quality data and very well engineered features when it comes to the machine learning algorithms. In this case, we took another paper. So you can understand that as a lab, we like to break other people's toys. This is our perspective, and we are very efficient with that. Someone constructs something and we go and demolish it, and we are happy with that. They're not. And in this case, we took a work from other authors that you see here. They trained the algorithm using random forest 4.5 and KNN, nearest neighbor, to classify the URLs in a supervised learning scenario. The training and the testing data was comprised, as you can see them on the table, of 4 single class and 1 multi-class data set. Initially, they had very high accuracy models, but we will get to that on how we managed to reduce the accuracy. Because that student of mine was not really familiar with ML, he worked in Weka, so we had no custom code in this case. Again, we take a white box paradigm. We assume that the attacker has full knowledge of the environment and the system, and we're using a Python script to split the labels. Again, as normal, 80 for training, 20 for testing. We gradually influence the model in intervals. So we used in malware defacement, phishing, and multi-class percentage steps for contamination 1% intervals. In the spam dataset, which was something weird that happened, and I will get to that, we had to use bigger intervals. We even reached 75% of poisoning of the labels just to achieve something. Here you see our methodology. We separate the data points according to being benign or malicious. We divide them into data sets, 80% for training, 20 for testing. We randomly fill it only, in this case, a percentage of labels, and then we recombine the testing and now the perceived training data. And coming to the results, we cared about the classification accuracy, precision, and recall. And as I said, we were going with 1% intervals when it came to label contamination. We found out that in the multi-class, C4.5 was the most degraded, and you can see that illustrated in the picture, while RF and KNN perform very similar to each other, but not they were not so robust to the attacks anyway. And we found out that KNN was the least degraded with those attacks. Coming to the malware dataset, here the performance is more similar with everyone. 4% was the sweet spot. So we were trying to identify where we made a real difference, where the drop was huge and we didn't have to invest a lot of resources from the attacker's point of view. And you can see it being illustrated there in the plot as well. And again, in this case, KNN was the most efficiently degraded at 6% of the labels, and RF at 7%. So they were a little bit more resistant compared to C4.5. In the phishing dataset, again, the C4.5 was the victim. It degraded way faster than the others. And in this case, KNN had to reach 10% of the labels flipped to being impacted, to have a 3% loss. So you understand that it was more resistant. Defacement, similar behavior, but KNN was the most degraded here. So you can see that according to the data set, we have different results that has to do with different things. It can be the balance of the data set, it can be the features that we have selected, and so on. The performance was very similar, and this is where it triggered us. This is where we said that something is going really wrong, because when it came to the spam data set, we were constantly changing labels and it was not happening. And because it was the smallest data set and the most unbalanced, that might be the reason. So you see here that we had to invest a lot of resources, like up to 75%, to make a difference. If you were an attacker, you wouldn't do that at all. It's a waste of time and of your resources. And coming to our final use case and the financial series models, which is the latest publication, and I will explain why it's the most important of all, is because all of those automations are being used daily in investments. And because that student used to work for the investment sector, they were like, when I talked about adversarial attacks, etc., they were like, okay, this is the most important thing we have to investigate. How can we influence the money flow around the world? So we have models that are trying to predict, and that's how we invest. We say, okay, AMD came up with a new graphics card, so it means that they will have more sales and people will invest on them, so the stock will go up. I have to buy more AMD stocks. And this is the forecast that we get from automated tools. But if we can influence them, what is going to happen? And this is what we did. We got financial stock data from Kaggle, and they were like from 2006 until 2018. We used a one-dimensional convolutional neural network model, and the training was 2006 to 2014, and we used the rest of the data for validation. We had a sliding window of approximately 30 days and a future price prediction, which was of approximately 14 days. The data was normalized so that each entry in the time series was the price difference from the previous entry. And this is what we call as the price delta with a Greek letter. As attacks, you see the algorithm here, and I don't have to dive deeper into them. We use the fast gradient sign method. We use the single value attack, which is a novel one. And we also use the very, very, very familiar label flipping attack because it's very easy. And why not? This is what initially was happening with the prediction model. You see that the sell confidence was 99.9%, while the buy confidence was 100%. Okay, you can understand the accuracy of making financial decisions based on this model. And then, with a single value attack, we reduce the confidence of sell to 92% and the confidence of buy to 97%. And you see how the models were affected in terms of accuracy with all the attacks. And the drop is obvious in everything, depending on the epsilon value. And then, using FGSM, look at the profitability. What is the base profitability? And according to our influence and the data points that we are reaching, how low it can be, how much we can drop it. Imagine the loss of money or the benefit for an attacker, for someone who manipulates the system with that model. Okay? And you see here the label flipping. You see the base model and how it goes up, and the label flipping performance, how it goes down. And again, although it has a bump, it's way lower than the anticipated. In every case, we talk about white box attacks, so it means that the attacker has access to our model. And we believe that if we had more time to fine-tune it, it would be more effective as well. So we talked about ML, we talked about attacks against ML. We checked 3 different application domains, and more are coming on the way. We are just stuck in the publication process. And we can draw some conclusion from all of those application domains, that the machine learning algorithms greatly rely on the quality of the training data, because without a good input, we don't have a good output. Someone who is privileged, they can change the perception of the machine about reality and thus create misclassification. We saw many different attacks, and how effective they can be under different scenarios and under different data set. So what does it mean? It means that we have to mitigate against poisoning and come up with defensive techniques. What we are currently doing as a lab, we try to perform attacks in different data sets and classifiers because we like to break things, as I already told you. But our main concern is to investigate the attacks from the defender's point of view. A popular methodology that has appeared in the wild and we have used many times is retraining the model using adversarial examples, with the problem being that if the adversaries change their modus operandi, the way they operate and the way they poison the model, we will reach up at the same dead end. We end up having a poisoned model, and we have to retrain it again and again. So this is what we are trying to fine-tune. What would be the trigger or the time window for that retraining to happen, or if we can use another approach where, for example, we fabricate or we orchestrate attacks ourselves, and that's how we can make the model more robust to poisoning attacks. And that was it. Any questions?
Thank you very much. Thank you very much, Nikos, for the presentation. Please stop sharing the screen in order to check if there are any questions from the audience. This will help me. If there is any audience, please raise your virtual hand. There is a reaction button in order to ask the questions to Nick. Nick, please stop sharing the screen if you don't mind. Excellent. I have some questions, but I'm not going to wait for the audience. I will start with mine. So I have a question. You mentioned something very crucial, that it's the input, the quality of the input that defines, the quality of the output. Because then, you can have these intrusions regarding the quality of data. So my first question is how do you define the quality of the data even before you are going to have the output? What are the parameters, the indicators that says to you that these are good quality of data? Is the volume? I don't know. You will tell me. I have no idea. And then my question is the following. My second question is the following. Since artificial intelligence, and this means the machine learning, provides sometimes answers and solutions that they are out of the box. Sometimes we cannot even realize how you can judge that this proposal and this outcome is a good one or is a malicious one. I mean, still I'm providing this example from the Kissinger's book about artificial intelligence, that the machine learning has proposed to the F-35 fighter pilots some maneuvers that the fighter pilots, they don't trust because it's out of their realization, but the data is correct. So what are the criteria to judge the outcome since it's out of the box, and how you can comment and judge the good quality of data before the outcome will come?
So in general, we cannot predict. The whole process is trial and error most of the times. And even research-wise, the papers that are being presented by ML experts, because I'm not taking myself as one, they are more fine-tuned. And this is the arms race in the ML domain. They are trying to fine-tune the models, make them more robust, faster, more effective, and so on. The quality of the data, it has, from the cybersecurity point of view, it has to do with the collection of the data. So if no one can interfere with the collection phase, it means that what you are collecting is representative of the real world. Then, how you process them to achieve the best output, it has to do with fine-tuning the model. It has to do with experimentation in contained environments. This is what we do usually. So again, from the cybersecurity perspective, we don't release something in the wild and wait to see what is going to happen, because chances are you will get an attack and it will be successful. You do it in a contained environment, a sandbox environment. You're trying to check how it's going to influence a virtual model. And here is where digital twins are coming in the picture in our days. So it's we used to have the sandboxes, we used to have the virtualization. Now with the digital twins, we can have the whole replica of the domain, and it massively helps us in that aspect. This is where we perform the tests, and we're trying to anticipate the next move of the attackers. We should not forget, though, we have to remain innovative in that arms race. Back in the day, most organizations were waiting for an attack to happen and then see how they were going to mitigate it. However, this has changed massively, because now all the major companies, and especially because I talk about financial data, especially in the banking sector, they have their own red team, which performs the attacks, and they have their blue team, which creates the defensive measures for the attack. So the major organizations that can sustain huge losses from cyber attacks, they are trying to predict that from happening, even in the ML level. They are trying to position themselves into the attacker's shoes and see how innovative they can be. Of course, the ugly truth is that we cannot predict everything. Especially in Scotland, we had even in the past year, I think we had 2 major cyber attacks affecting 2 universities, with one of them making a speedy recovery, the other one they still have issues. We were usually recently attacked, and we managed to mitigate because we were expecting it. So it's happening every day. You can never be sure about the effectiveness. What you can do is train your model in, as frequently as you can, fine-tune your model, upgrade it, use better hardware. We are crossing another era. So from quantum computing, we are going to the quantum inspired, where we can use the quantum algorithms in normal PCs, and this might make a difference as well. But expect also the attackers to adopt those methodologies. So it's a constant arms race.
And now, I have another one, in the electronics, in ordinary optoelectronic systems, in order to collect and control the quality of the outcome, we have, these feedback loops, So in this case, I mean, you should wait, you say try and error. I mean, you mentioned something that you input, you have the outcome, and then you try again. I mean, how long you should wait? I mean, you should wait, to collect, a vast volume of data in order to check out that the outcome is not the appropriate one or not the desired one. I mean, what kind of checks you are doing in between before you spend so much effort?
Depends. Usually, the intuition is the more the merrier, but the more data you collect, the more massive resources you need to process them. So it depends on the application domain. In some application domains, a minimal data collection might be representative because of the things, for example, the devices can perform, the actions they can perform. So if we have a very simplistic IoT device with 3-4 functionalities, we know what can be produced from those functionalities, essentially. And the data collection will be minimal. If we have a more complicated environment with different IoT sensors, devices, and so on, this grows exponentially. Okay, so it depends. When back then, when I was doing my postdoc, we were collecting passive DNS data, and the more we were collecting, the more robust decisions we could make in the experimentations, because we have a better representation of the world, and especially a better representation of what the actual users were doing. And this is what is difficult, I think, with across all of our domains. Maybe in your domain, you can represent what is really happening, and you can have a more intuitive approach to the everyday and to the real world settings. But in the cybersecurity domain, a lot of times we have to go with fabricated data, and because we cannot get our hands on the actual data due to privacy concerns, due to a lot of things. So yeah, there's no definite answer, because as I said, it depends on the application domains and on the diversity of actions that we can have within that domain.
I was expecting that there's going to be a checklist, before someone feed the system with data, who is the provider of the data, in order to prohibit, intrusions, no?
This is one of the issues we are trying to solve with Trustee, that we are working with the Hellenic Mediterranean University and other partners across Europe. So it's one of the issues we are trying to solve. Who provides the data? Can they be accountable for providing those data? When those data stop being efficient, they stop being representative of reality, who can make use of them, and if they can be privately protected, so that other scientists across the European space, they can make use of them. So these problems exist, but we are on the process of solving them.
Okay. Thank you. Thank you very much, Nikos, for the answers. Any other question? I can see Antanas. Antanas is a professor in Vilnius Tech, if I remember correct.
Yeah,
Antanas, the floor is yours.
Correctly, okay. Yeah, some general remark that it seems that it is reality that or to say the quality of our systems will be dependent on the quality of data sets, and not only quality of data set, but the trustworthy of the data set. So it seems that we will need some kind of, okay, can call certification system, because always we will use some third-party data sets. You cannot collect all data yourself. And even if you are collecting yourself, you are using some kind of tools which are provided by somebody else. And so the trustworthiness of the data sets is becoming a crucial issue, as I can understand from the talk. So, and it seems to me that we will need some kind of, how to say, certification and some kind of, let's say, digital signatures for data sets, if I can generalize that. Because for adversary effectively to corrupt your system, they will need, okay, it depends, but they will need some kind of access to the data set. Is it correct?
Yes, that's correct. And as I said, it's one of the issues that we are trying to solve with within the trustee consortium and within the trustee project is one of our main concerns. Another concern that I would put, and this comes from my early days of my PhD, is the malicious insider threat. So regardless of how good data we have collected, if we have an employee who is not monitored regularly, and we don't anticipate their actions, it means that they can influence the data. And here where the problem exists, because from the birth of the ICT systems until now, one of the issues that we haven't come up with really robust ways is the malicious insider threat, because we cannot predict that someone who is abandoned by his wife and kid the next day will come to work in a very, very adversarial setting in their mindset and will cause trouble. So data, collecting the data, creating trust during that collection process and distribution process is one aspect, but the other aspect is also the insider threat and how we can be sure that the persons who are responsible to oversee the whole process, they're also robust to potential influences from their environment.
Yeah, but the answer is that you cannot achieve that. It is fundamentally, you cannot be sure that Sam Bankman-Fried is a, how to say, guy whom you can trust. It's impossible. If the boss of the company, how do we be sure that we can trust boss of the company?
Well, that's true, and this is why most of the, and against it lies to ML, most of the systems that are tracking the behavior of a user within the scope of a certain organization, they are checking for abnormal activity. So if suddenly I start deleting databases, although I would not do it in my everyday tasks, at least it will prevent me from deleting a lot more databases. So okay. I think we have reached a point. I know that we cannot prevent the malicious insider threat, but we have reached a point that we can minimize the impact compared to the previous decades.
Yeah, I agree that I was semi-joking. This is not too serious, but this is like that you cannot avoid phishing and spam completely, because there are no clear line what the difference of legitimate email is and spam. Because for somebody this is how to say wanted mail, and for others this is spam. So it's no chance to solve it finally. You can only just, how to say, improve up to some extent. So
that's true, and it has to do with the technical or the cybersecurity awareness of the employees, and this is why it's becoming more popular for all major organizations to invest on awareness and awareness classes, so that the employees can get as much educated as possible in the latest trends. Because honestly, all of us have fallen a victim of a phishing attack at some point, although we managed to understand that it was phishing in the middle of the attack. You know, when you were about to insert your credentials, you were like, this doesn't make sense. They wouldn't ask me for that. So increasing the awareness is another thing to prevent phishing attacks from happening. But still, I would say we have a long way to go. I detected something, it was a phishing attempt on myself. It happened like a month ago. And although I conveyed that to my parents, they were, you know, they were eager to do the same mistake within the week after I told them what happened with me, because they couldn't understand, they couldn't port my my case to their phishing email. They thought it was relevant, it was legitimate, and fortunately, I stopped that last minute from happening, because they asked me, they were like, "Does it seem phishing to you?" And I said, "Obviously," but again, as I said, I almost fell a victim myself the previous week. So it's all about awareness. It's all about your clarity at the time that you're checking an email or checking a website. It's happening. The only way to protect ourselves is put as many defensive measures as we can. So having some, if we are not users with a high tech background, it's good to have more software to assist us when it comes to antivirus software or whatever else. In that case, if we are more advanced users, yes, we can have a better understanding. But again, the more artillery we have from our point to defend ourselves, it's better in the e-world.
But you know, in this point, Nick, I would like to ask your opinion and a very fast answer in order to close. I mean, how the blockchain technology can protect us from all these intruders?
So, because we are also using a lot of blockchain solutions, and it's an integral part of the lab, blockchain is not the silver bullet. Okay, it is a trend. It used to be like AI is in our days. It used to be like that 4 years ago. Everybody was talking about blockchain. It has been advanced, it can be implemented, it can offer a robustness, it can offer accountability, it's tamper-proof, but at the same time, if not used correctly, it can create a lot of overhead, a lot of energy consumption without a particular reason, and it can put us into trouble. So the combination of blockchain with other cybersecurity solutions that we have inherited from the previous years might be an answer, but it depends on the problem. In the scope of Trustee, we are using blockchain for accountability. So we are recording the actions of or the transactions of everything that is happening within the ecosystem, and we are storing that information, we attach it to a blockchain. The reason is that it's tamper-proof, as I said, nobody can interact with that. And in case something goes wrong, we can go back in time and we can have an audit trail. This is the best way the blockchain can help us.
Yeah, this is correct. I mean, there are a lot of also concerns on CO2 consumption with all these IoT devices connected as well, because this is energy consumption as well, but this is another talk that we can make. At this point, I would like to thank Nick Pitropakis for this very nice presentation. We will continue next week with another cybersecurity related talk from our colleague, Professor Evangelos Markakis, that is going to present how cybersecurity can protect big facilities. But until next week, I would like to wish to all of you a happy weekend. Thanks, Nick, for your contribution. All of you for your participation, and I hope that we will meet again next week in one more Athena talk. So thank you and stay safe. Bye.
Thank you.
Bye.
Bye.